Hello, y'all. Welcome to Lesson 6, Structure S 1.2.3. This is our first HL lesson of the DP curriculum. We are covering mass spectrometry, which is where we use mass spectra to determine the relative atomic masses of elements from their isotopic composition. So we will be able to interpret mass spectra in terms of identity and relative abundance of those isotopes. And that is basically what we will be covering today. We'll also be doing two examples of problems that the DP might ask at the end. So stay tuned for that. So first, what is mass spectra? Well, mass spectra uses a mass spectrometer, which is an analytical device used to determine the MZ ratio of isotopes in a naturally occurring sample of an element. So we have a couple words there that we need to highlight. The first one, of course, is isotopes. We remember from our previous lesson, isotopes are different atoms of the same element, but they have different numbers of neutrons. So isotopes have different neutrons. The other one is MZ or M over Z ratio. So what does that actually mean? Well, MZ is actually the mass to charge ratio of an ion. Now, when we're talking about mass to charge ratio, we literally mean mass divided by charge. And within mass spectra, most charges are plus one. Therefore, mass divided by plus one is just mass. So usually when we do an MZ, it gives us the mass of the ion. And we're saying the relative atomic mass or even the mass number. All right. So then the other thing we're going to talk about is how mass spec works. Generally, we abbreviate to mass spec. Now, the DP will not test on how mass spec works. You won't have to truly understand it, but I think it's a good thing to cover. So the first thing we do is we vaporize a sample. Vaporize a sample. Step one. So we turn it into a gas. So vaporizing from our previous lesson means turn to gas. Then we ionize the gas. And we do this usually with high energy electrons. And we ionize the gas into ions and sometimes molecular ions, which just means a compound that is an ion, a molecular compound that's an ion. Then we accelerate the gaseous ions. And we're going to do that in an electric field, in an electric field. Then step four, we are going to deflect the ions with an electromagnet. So we're going to use a magnetic field caused by an electromagnet to deflect that flow of ions. Lastly, step five, we will detect the deflection. What this basically means is things that have a low MZ ratio deflect a lot, deflect a lot. Things that have a high MZ ratio deflect a little. So generally, we can also understand that a low MZ ratio means a low mass, a high MZ ratio means a high mass. And you can kind of understand why. If we are trying to deflect something off its path, it's easier to deflect something that weighs less than something that weighs more, because something that weighs more takes more force. Anyways, let's pretty much move on from there. So, what does this actually produce? Well, when we do mass spec, we get a graph. So let's start with an example. So in mass spec, so let's say maybe the exact mass spec of lead, which gets converted into lead gas ions. So they will become +1 ions. So Pb is lead, just in case you don't have your periodic table handy. When you run lead through a mass spec, you will get a graph of values. And the graph for mass spec is very important to know the axes. So on our y-axis, we have percent abundance. And on our x-axis, we have our MZ ratio. So I'm going to pause the video here and fill this graph in with the values. So once we have this filled in graph, we notice a couple things. We have a peak at 204, a peak at 206, a peak at 207, and a peak at 208. So this tells us the main isotopes of lead are Pb204, Pb206, Pb207, and Pb208, with the most common isotope being lead 208. So when we look at this graph, we see that lead 208 has a 52% abundance. We can automatically predict, so we can make a prediction of our relative atomic mass for lead. So if you were to make that prediction, pause the video and make a prediction now. I'll give the answer in 3, 2, 1. So I predict my answer to be somewhere right around here, a little bit past 207, mostly because I have a lot of 208 and about more than twice as much 208 as I do 206 and 207. So my guess is going to be like around 207.1, maybe all the way to 207.5, something like that. Somewhere in that range. What the IB or DP is going to ask you to do is then they're going to ask you to actually calculate our relative atomic mass. And if we remember how to do that, pause the video and try and calculate it yourself. But otherwise, I'm going to go through it right now. I take the mass of each isotope and multiply it by its percent abundance. Now, when you convert percents to numbers, you pretty much divide that by 100. So we're going to add that to 206 times 0.24 plus 207 times 0.20 times 0.22 plus 208 times 0.52. When I do all this math, I get a mass of 207.22. So I find that my prediction was pretty darn close. I would say I was in that range quite all right. So this is what mass spec is going to give you. It's going to give you a graph of the percent abundance of each isotope at its relevant mass over charge. So that's one thing that I do actually want to be clear on. When I write these values for lead, these are actually lead +1 ions that are being detected because our mass spec only detects ions. All right. So that's mass spec. It's pretty plain and simple. But now we're going to extend it past to the mass spec of diatomic elements. We briefly mentioned that there are some elements that are diatomic. What that means is that these elements naturally occur in bonded pairs. So they always occur as a pair of two. And there are 7 diatomic elements you must remember. They are hydrogen, oxygen, fluorine, iodine, nitrogen, bromine, and chlorine. I remember it with the phrase Hoffenberkel. Now, I like Hoffenberkel because it sounds kind of stupid, but because it sounds kind of stupid, I've remembered it my entire life, starting in ninth grade so many years ago. But Hoffenberkel are your seven diatomic elements. There are many others like have no fear of ice cold beer, have no fear of ice cold beer. The nice one about that is that it tells you a couple things. First off, it tells you that beer is a liquid, therefore bromine is a liquid. Um, in addition, iodine can naturally be found in a solid because ice is solid. So it gives you a couple cool hints. No matter what you want to use, just remember that these are your seven diatomic elements. So the reason I went through this is because diatoms act a little differently in mass spec. So let's take chlorine as an example. So chlorine likes to appear as Cl2, and chlorine is already a gas. So when you ionize it, this becomes Cl2 plus. Now, chlorine plus is unstable. So in the mass spec, it will sometimes be Cl2 plus, but other times it can break up into Cl plus and Cl. Now, that presents an issue. First off, chlorine will not appear. It will not appear because it's not an ion. And mass spec will only deflect and measure these ions. So what you're going to get is a mixture of chlorine 2 and chlorine. A couple other things about that is we get a different graph because chlorine 2 has a mass of somewhere around 70 to 74, while chlorine has a mass of 35 or 37. The two naturally occurring isotopes of chlorine are chlorine 35 and chlorine 37. So when we have these two isotopes, we get an entirely new graph. So let's go ahead and sketch that out. Now, I'm going to pause it again, and when I return, we will have a graph. All right, so we have this sort of mass spectra. Now, it's a little different than the one we're normally used to. So first off, these are going to be values that are relative to one another. So our highest value is going to be at 100%, and that is what we call our base peak. Now, a couple things about that base peak. We notice it's at 70, meaning that the thing that made this has a MZ, which is basically equal to the M of 70. That could only be made with Cl35 isotopes. Therefore, we know this base peak is made from the diatomic composition of chlorine 35. So we have two chlorine 35 atoms together. I'm going to change the color here just so that it all becomes a little more clear. Cl2 plus 35. Now, a couple things about that is we can then use it to determine what this next down peak is right here. This has a mass of 72. The only way we can get 72 is if we have a combination of Cl35 and Cl37 as our diatom. And lastly, 74 has a composition of Cl37 together. So we can identify these three peaks and the different isotopes that make up these diatoms here. Next, we have this peak of our fragments, our positive fragments, um, our ions. Well, it's quite clear that at 35, that must be Cl35. And over here, we have Cl37. And because we have this relative peak to each other, we can note that Cl35, the ratio to Cl37 is about 3 to 1. And if we were to do the math, we'd probably get something around our 35.45. 5. It's not exactly 3 to 1. That would have been 35.67, but it's not. So it's kind of close to our mass of Cl 30, sorry, 35.45. So this is how diatoms show up. We get an array of peaks where we're going to have some peaks at the individual ion fragments, and we're going to have some peaks at their diatoms based on the isotopes. And the more isotopes we have, the more peaks as this combination can change between different isotopes. All right, so that is it. What I'm going to move on to are two example problems, so two practice problems. So stick around if you want to work on them. If you don't, have a great day. So starting with number one, given a diagram, and I'm going to make this one super rough, at 20 and 21 mz and percent abundance. Like I said, super rough. We have a percent of 80.1 and a percent of 19.9. We have two questions. Question A is how many isotopes? And question B is what is AR? Our relative atomic mass. So you can pause it now, and I'm going to go over the answer in three, two, one. Well, clearly we have two peaks. This is not diatomic because we don't have two sets of peaks. So there are going to be two isotopes. Our element X20 and our element X19. Or sorry, 21. What am I doing? And then what is the relative atomic mass? Well, we just have to plug in our formula. So we have our mass 20 times 0.801 plus 21 times, whoops, should keep things the same, times 0.199. And when you plug that into your calculator, you should get a mass of about 20.2. All right, that is problem one. Problem two. We're going to ask you to sketch the diagram and calculate the relative atomic mass of ZR based on the following data. So when we look at zirconium, there are quite a few isotopes. There are going to be 5 of them. So we have ZR90, we have ZR91, we have ZR92, we have ZR94, and we have ZR96. And they have a relative percent abundance of 50, or sorry, just a percent abundance of 52%, 11%, 17%, 17%, and 3%. So we have to sketch this. Now, I'll try and be a little less rough here on this sketch, but it'll still be a little less clean than my other ones. I like to go through with 20s, 20, 40, 60, 80, 100. A couple things of note is you must have percent abundance on the y-axis, and you must have mass to charge ratio on our x-axis. You can kind of start that wherever though. So 90, 91, 92, 93, 94, 95, and 96. 93, 94, 95, 96. All right. And then for our actual data, 90 is our most common isotope, and that's right at about 52%. 91 is right at 11. 92 is at 17. 93 is also at 17. So I'm going to make that about the same height. And oops, sorry, I shifted these over. 92 is 17. 94 is 17. My bad. And then lastly, we have 96, which is 3%. All right, so there's our graph. We should always note what the graph is actually showing. So we're going to go ZR 90 plus. You cannot forget the plus. ZR 91 plus. ZR 92 plus. ZR 94 plus, and ZR 96 plus. You need to include that these are ions because we know that ions do show up on mass spectra while neutral atoms do not show up. So with that, we're done. Hopefully this helps you learn mass spectra and have a great day.